So one of the things that we can do talking about fluids is we can add a new force to the list of forces that we've talked about so far this semester. And that new force is the buoyant force. With the buoyant force, we're going to emphasize situations where we have a static fluid. So our fluid isn't flowing. But if you have an object sitting in a fluid, we have a new force called the buoyant force that is the net force acting on the object due to the fact that it's submerged within a fluid. So for starters, where does that force come from? Well, again, if I think about my cube, and now instead of a cube of fluid like we've talked about in the last couple of videos, this is a cube that happens to be some object that's sitting submerged in my fluid. So I know that the top surface of that cube sits at some depth within the fluid. There's a pressure at that depth. That pressure is going to be due to particles as they run around. Those particles are going to generate a force that acts on the top surface of my cube pointing down. At the bottom of the cube, it's the same idea. It's just that those particles are going to bounce into the cube and bounce off, and so they're going to generate a force that points up. And because I know that the bottom of my cube is at a lower depth within the fluid, it's got to be a greater pressure, which means there's going to be a larger force. On the left-hand side, same thing. Again, I can, even as I come down the cube, I can use calculus to figure out what the total force is acting on that left-hand surface. I can do the same thing to figure out what it is on the right-hand surface. I can do the same thing for the surfaces on the front of the cube and the back of the cube. So I can basically think about there are 6 different forces acting on my cube as it sits submerged within this fluid. And so all I want to do is add those up. So the buoyancy force is the net force due to the different pressures acting on all the surfaces of the fluid. And so I know that there's going to be a force at the top that points down, a force from the bottom pointing up, a force acting on the left hand of the cube that points to the right, the force acting on the right hand of the cube pointing to the left, a force on the front surface pointing towards the back, and a force on the back surface pointing towards the front. Well, the nice thing about this being a cube, and this is true in any situation, it's just much easier to see within a cube, is that of course the forces on the left and right, they're equal in magnitude, they point in opposite directions, they're going to cancel out. That's also true for the forces on the front and the back. Right? The force in the front points towards the back, the force in the back points towards the front. Again, those are going to be equal in magnitude and opposite in direction. And so what I'm left with are only forces that act vertically. And so in this case, I'll just happen to label that as the y direction here. I know that I've got a force from the bottom pointing up, a force from the top pointing down, and so the buoyancy force is just what do you get when you add those together. And so when I sum those together, I've got a force acting on the top of the cube that points down. Given my choice of coordinate system, that's going to need a negative sign in front of that one. A force acting on the bottom of the cube that points up, so that needs a positive sign. Those forces can be written as, so if pressure is force per area, then the force is equal to pressure times area. So I've simply rewritten the magnitudes of those forces in terms of the pressures. And again, what I can do is I can just rearrange this, and what I'm left with is that the difference between those pressures is nothing more than the density of the fluid times the gravitational acceleration, 9.8 meters per second squared, times the height of my cube. So the difference between the pressure at the top and the pressure at the bottom really only cares about, well, how much farther does the bottom surface sit than the top surface, and that's just the height of my cube. And again, I can combine that height h and that area a, and that's just the volume of the cube. So in this case, I get that the buoyancy force is equal to the pressure of the fluid times gravitational acceleration times some volume. So what we're going to do is we're going to rethink the buoyancy force. I don't want to have to think about sort of a multitude of forces each time. I just want to think about what their summation is, and I know that summation is going to give me something that points up. So the buoyancy force is going to be a force that we can think of, even though it acts over the total surface area of the cube, I can think of it as acting up, pushing on the bottom of the cube, trying to keep it from falling. So in terms of thinking about our forces, we started by saying for any force we were going to deal with, there's some question that we want to use to think about whether or not that force needs to go into our free body diagram. And so since the buoyant force obviously deals with fluids, the relevant question cares about, is your object submerged in a fluid? If the answer is yes, then you need a buoyant force in your free body diagram. In terms of what the magnitude that is, the magnitude of the buoyant force is equal to the weight of the fluid displaced by the object. So this is what's known as Archimedes Principle. So you'll notice here that we've taken the density, that density of the fluid, and the volume term, and we've combined them. And then there's one little difference that we've added here, is that what we actually care about is not any old volume, and it's only the volume of the object if your object is entirely submerged. So what the buoyancy force really cares about is the volume of the fluid times gravitational acceleration times the volume of the fluid that's being displaced. So if your object sits entirely below the surface, like it did in the previous picture, or the picture on the previous slide, then the volume of the fluid that's being displaced is equal to the volume of the object. On the other hand, if you have an object that's only partially submerged in a fluid, so an easy example to think of here is, say, something that's floating, right? So if it's floating so that some of the object sits above the surface of the fluid, the rest sits below the surface of the fluid, well, then the volume of fluid that's being displaced is not equal to the volume of the object. It's something less than that. In terms of direction, the buoyant force always points up. So these are sort of the parameters that define the buoyant force. So let's look at a couple of examples. So let's start by taking an example where, again, here's my cube. It wants to sink to the bottom, so what I'm going to do is I'm going to hold it in place by attaching a string to it. And so if I think about the free body diagram of that cube, again, I know that the cube has mass, so there's going to be a gravitational force pulling the cube down. It's not in contact with the surface, so I don't have to worry about either a normal force or a friction force. There is a string that pulls on the cube, so there's going to be a tension force that's going to point up. And then, is the cube submerged in a fluid? The answer there is yes. So there's going to be a buoyant force that's also pointing up. I know that these forces have to cancel out, so to set up my equation, I'm going to pick a positive direction. I'm going to get that the net force acting in the y direction has got to be equal to mass times the y component of the acceleration. It's not accelerating, so that's got to be 0. So I've got the buoyant force, which points up, the tension force, which points up. Both those will be positive, minus the weight because it points down. At this point, I know that I can plug in for the weight, mass of the object times gravitational acceleration. And I know that I can plug in for the magnitude of the buoyancy force, again, the density of the fluid times the gravitational acceleration times the volume of the fluid that's being displaced by the object. So the question is my object entirely submerged? The answer here is yes. So I know that the volume of the displaced fluid is equal to the volume of the object. So I get that the buoyant force is equal to the density of the fluid times the gravitational acceleration times the volume of the object here. So I can plug all that into my Newton's second law equation, and I'm left with this expression. So I've got the term for my buoyant force sitting out front, the tension here, again, I don't have an expression to calculate that. Newton's second law is going to tell me what that is, and then I've got this here to tell me what the weight is. Now, one thing to highlight is that if you solve this for the tension in an equation like this is known as the apparent weight of the object. What that means is, if we were calculating the weight of the object through that string, so say we had this string attached to some spring scale, that scale was telling us what the weight of the object was as it hangs there in the fluid, well, that wouldn't be equal to the weight of the object because you would also have that buoyant force that was pushing up. So the tension force here is what's known as the apparent weight. It's how much lighter does this object actually appear to weigh than what it really weighs because of how the buoyant force is helping to hold it up. Let's look at a second example. So here, instead of having that object completely underwater so that it wants to sink towards the bottom and I'm holding it up with a string, Here I've got an object that's floating. And so again, when I think about my free body diagram, my object has mass, so I've got a gravitational force pointing down. It's not in contact with the surface. There are no strings or anything else pushing on it. The only other force that acts on it is the buoyant force because it's submerged within a fluid. So again, I can pick my coordinate system, let positive y point up, and set up my equation. And Newton's second law here tells me that basically the buoyant force has got to be equal to the weight. So I know how to calculate the weight. Again, that's mass of the object times the gravitational force. And so, of course, the buoyant force is the weight of the fluid that's being displaced. And so that's the density of the fluid times gravitational acceleration times the volume of the fluid that's being displaced by my object. Again, my question, is the object entirely submerged? In this case, the answer is no. So here, the volume of the displaced fluid is not equal to the volume of the object. It's some fraction of the object's volume. So when I plug what I can do with the magnitudes for my forces back into my Newton's second law equation, I get this expression. And so here there's a couple of details. The most notable, of course, is that displaced volume is still an unknown. It's not the volume of the object. And so what often happens is that, again, I can think about dealing with this mass term, and again, think about the mass of the object is the object's density times its volume. And so if I plug that in for the mass, notice what I get is two terms that look a whole lot alike. I take one to the other side of the equation, I cancel out the g's, and I can figure out that the volume of the displaced fluid here has got to be equal to the ratio of the density, so the density of the object over the density of the fluid, times the volume of the object. My object is floating because the object's density is less than the fluid's density. So when I think about this ratio here, I know it has to be something less than 1. The density of the object is less than the density of the fluid, which means that ratio is something less than 1, which again tells me that the volume of the fluid that's being displaced is less than the total volume of the object. And again, the greater you make the density of the fluid, the more that buoyant force is able to push up, and so therefore the less of the fluid that needs to be displaced to make the object float.